I am going to discuss full adder design from the digital logic design or digital circuit. The full adder is a combination circuit that is used to add 3-bit binary numbers. In case of half adder, we can add only 2-bit, 0 plus 1, 0 plus 0, 1 plus 0, or 1 plus 1. But in case of full adder circuit, we can add 3-bit. So what is the problem with the half adder? In half adder, we can add 1 plus 1 means 0 and sum is 0 carries 1. We can add 0 plus 1 means sum is 1 carries 0. But in case of full adder, what happened? 1 plus 1 plus 1 suppose and 1 plus 0 plus 1, we have to add these numbers. Then what happened? 1 plus 1, we can use half adder, that is mean 1 plus 1 equals 0 and there is a carry. So in this addition, we need 3-bit. Half adder cannot add this 3-bit. So we need 3-bit adder, that is full adder. So let us consider the designing process of a full adder. First point is, full adder has 3 inputs. It has 3 inputs, A, B, and third one is C in. C in means carry in, and 2 outputs. Sum and C out mean carry out. So every adder must have 2 output, that is one for sum of this bit and another for carry in C out. So this is the first point. Now the second point is block diagram. Block diagram, it consists of input, that is A, B and C in. These are inputs, and this is the full adder, and these are the outputs, mean sum and carry out. This is the block diagram. These are the outputs. The third point. Before going to design this full adder, we need a combination, input combination to output combination. The truth table in digital circuit is used to represent the output values with the help of input combinations. What are the possible inputs? Now the truth table. The inputs are here A, B and C in. A, B and C in. And outputs are sum and carry out, C out. So this is the truth table. And we know if there are n variable in the input combination, then there will be 2 to the power n combination of outputs. This is the rule. N variable means suppose n is 3. Here n is 3. So we have to find out how many outputs? 2 to the power 3 equal to 8. So there will be 8 combination of inputs. 1, 2, 3, 4, 5, 6, 7, 8. 7 and 8. The decimal values are 0, 1, 2, 3, 4, 5, 6, 7. So these are the number of rows. These are the decimal values of that rows. Now put the value of 0, 1, 0, 1, 0, 1, 0, 1. Then next 0, 0, 1, 1, 0, 0, 1, 1. And the next one is 0, 0, 0, 0, 1, 1, 1, 1. In the first LSB bit, that is the LSB, least significant bit, there is a 0, 1, 0, 1, 1 gap. In case of next bit, that is the LSB next bit, and it will be 0, 0, 1, 1, 0, 0, 1, continue. And in case of third bit, that is 4, 0, 4, 1, 4, 0, 4, 1, continue. In case of suppose there will be 4 bit, then it will be 8, 0, 8, 8, 1. 8 1 8 0 8 1. So here the 1 0 0 1 0 1 0 0 1 4 4 0 4 0 4 1. Now we have to find out the sum and carry. What is the values of sum and carry? First of all, we have to add 0 plus 0 and we get sum is 0, carry is 0. Now next bit is 0, so 0 and 0. The sum is 0, carry is 0. In case of this one, this is the 0 case and this is the next case. Means 0 plus 0 means sum is 0 and there is no carry, and then the next one bit is added. 0 plus 1 is 1 and there is a carry 0, mean 1 0. And third one mean that is 2. 0 plus 1 means sum is 1 and there is no carry, and next again 0 plus 1 and carry is remain 0, 1 0. and the fourth one actually the third values. 0 plus 1 equal to 1, and there is no carry, then 1 is mean 0 plus 1 plus 1 equal to 0, and there is carry mean 0 plus 1 equal to 1, mean sum is 0, carry is 1. Now the fourth one, 1 plus 0 equal to 1, and there is no carry, and then 0 mean 0 plus 1 equal to 1, and there is no carry mean 1 0. And the fifth one, 1 0 means sum is 1 and there is no carry, then 1 plus 0 means 0 and there is a carry, and 0 plus 1 equal to 1, that is equal to 0 1. And the sixth mean that is 1 plus 1 equal to 0, carries 1, and then 0 is added, 0 plus 0 equal to 0, and 1 means sum 0, carry 1. And finally 1 1 and 1 plus 1 equal to 0, sum is 0, carries 1, and then next one is added, we will get sum 1 and carries remain 1, meant 1 and 1. So these are the input combinations. According to input combination we get the output combinations values. So these are the output values. Now we have to find out the circuit, that is we need to find out the Boolean expression. Before going to design the circuit, we need to construct the Boolean expression. We can design Boolean expression with the help of manual way, or we can use K-map. K-map is the most simplification technique that generate most simplification expression values. So we can use here K-map. Now next point is the fourth point, K-map. K-map for S. Now this is the S the output combination values. Now this is the sum of product. So in case of 3 variable K-map, there are 8 cells. So this is 1 2 3 4, and this one row, there are 2 row and 4 column, and this is the A bird A, and this is B bird C in B bird C in bird, B bird C in B C in, and B C in bird. So this is the structure of the K-map. So B bird C in bird, and B bird C in B C in, and B C in bird. Decimal values are 0 1 2 3 4 5 6 7. This is the construction of 3 variable K-map. Now we have to put the value. We have to put the values of 1. So this is the 1 in 1 values. We put the value of 1 in 2 decimal places. That is 2 decimal value, 2 positions. That is 1, and second one is in 4th position. One put the value of 1, and this is 7 1. So there is not possible to group the 1. So we will consider individual 1. That is, this is the 1 value. So we will get the simplification values. S equal to A bird, B bird, C in. Next one is A bird, B, C in bird. This is the second one, and third one is A, B bird, C in bird. A, B bird, C in bird. And fourth one is A row and column. The intersection values are A, B, C in. So this is the expression. Now we can minimize this expression, which taking some common values. A bird, B bird, C in, B, C in bird, plus A mean B bird, C in bird, and B, C in. Now this is the expression for XOR gate. This is B, C in, and this is the expression for XNOR gate. XNOR gate. Now we know the XNOR is a complement of XOR. XNOR is a complement of XOR. So we can perform the complementation of these numbers. Now this is again the XOR operation for A, B, and C in. So this is the sum expression. This is the output for sum, and the Boolean expression for sum is A plus B XOR C in. A XOR B XOR C in. Now we have to find out the K-map for carry in C out. Now finally we can design the circuit from the Boolean expression. Now the K-map for C out, I am writing here. K-map for C out means this is the for third variable K-map, that is second A bird A, B bird C in bird, B bird C in, B C in, and B C in bird. 0 1 2 3 4 5 6 7. Now putting the values of 1 in case of C out column, mean third 1, there is a 1, and there is a fifth fifth one is 6 1 and the 7 1. Now we can group here, can perform the group between the 1. Now we can perform the group. There is a group, there is a group, and there is a group. So C out equal to column wise BC in plus row wise A common, and there is a C in, AC in, and this one is AB. So this is the Boolean expression for C out. Now we can finally design the pool adder circuit. In design means circuit diagram. So this is the last step of the pool adder circuit design. Now circuit diagram is the fifth point. Circuit diagram for pool adder. This is the circuit diagram for pool adder. Now this one is A, B and C. These are the inputs. Now we can perform XOR operation between A, B and then C. This is the sum, and for the carry out B, C in mean we can perform AND gate B, C. This is the B, C. Next one is A, C. A taking A and C in AND gate, and the third one is AB. A taking A and B. So these are the three AND gate. Now finally add those AND gate to get the result of C out. So this is the circuit diagram for pool adder circuit. So in this, be very much for watching this video, share and subscribe it. Thank you.